I changed the title a little bit just to kind of, this is a multi-phase forum, so I just changed it a little bit, but it's kind of the same kind of talk. So my name is Jia, currently at Chalmers. Gonna get started with so this is the outline of the talk. Gonna start with the how fluidized bed scale up is done. I'm gonna review 100 years and then kind of walk through how it's progressed through the decades. And then we're gonna talk about challenges and enablers. What are the challenges right now and what would help us expedite this scale up challenge? And then we'll end up with some concluding thoughts. So first 100 years of commercial fluidization. So as people in the field should know, we celebrated 100 years anniversary of the commercial fluidized bed in 2022. So this means scale up and optimization has carried on for 100 years, which means there's been a lot of effort going into decreasing the time to market, basically decreasing the time needed for scale up and decreasing the cost for involved in the scale up. So most of us would know that this the first commercial fluidized bed process is the Winkler coal gasifier, started in 1922, and then I'm gonna run through the key applications in during the World War II. This fluid catalytic cracking became commercialized because of the need for transport fuels. And this is one of the most important technologies that helped the Allied forces win the World War II. And as we moved on, plastics also became a lot more easy and cheap to be produced through fluidized bed. We've got the polyethylene and polypropylene. And then as the green consciousness came into place, we've got biomass gasification in the 1980s in Finland, and then in the US, there's this polysilicon process that has that made possible the price of solar panels to be a lot more competitive through using a fluidized bed to produce polysilicon. And as we moved on, I guess then the question is, it's been 100 years, is fluidized bed technology still relevant? And the answer is yes, because a lot of these green technologies still rely a lot on fluidized bed processes. So the fluidization processes or technologies that are still kind of very, very relevant for tomorrow, we're talking about 2020 onwards, all these buzzwords on sustainability, renewable energy, green chemicals, circularity, so on and so forth. For example, biomass to energy, plastic to chemicals, and so on and so forth. And these are still very, very, very relevant, and fluidized bed technology still underlies a lot of these new or up-and-coming technologies that are needed for us to get towards net zero. So then this need is still ever present, that we need to do scale up faster and cheaper so that we can have all these very, very nice technologies being implemented as soon as possible. So then how is scale up done? Just to put it in perspective, so this has been the case since the beginning. So it's stochastic. So scale up, as the name implies, is basically we're trying to go from a little scale, from a lab-based concept, and then we go to a slightly larger scale, and then a slightly larger scale, all the way until we get to the commercial application. So this process of going progressively to slightly larger and larger units until it becomes an industrial process, it takes on the order of like about 10 years. And then this is too slow for these time-critical sustainability challenges that we need to be kind of addressing like now. And so this is very slow because, as you can see, if we do this purely experimentally, after we get this very promising process, we need to build a larger reactor and then build another larger reactor and so on and so forth. And then historically it's been done in a linear sequence. And basically we don't do the kind of demonstration unit until the lab scale experiments are all completed. And so this linear sequence is very, very costly. And then once you get to a larger scale, visiting is very, very costly. So this is this is a key challenge, that this is how scale up is done. And this is tried and tested, but it's very slow and very costly. So then the problem, or as in, why is there a need to go so conservatively from a little scale to a slightly larger scale to a slightly larger scale, and until we reach the commercial scale, is because we know that there are these challenges that don't scale very well. So solids losses, if we know the attrition at a lab scale, can we automatically know what's going to happen at the commercial scale? No, because these don't scale according to the size. So entrainment rate cyclones. And then the representative scale, we know are these meso-scale structures that don't scale, are still not very well understood for us to be able to know what happens at the larger scale. And the other thing, like bed density and the other kind of very, very important phenomena in fluidized bed technology. And then the hydrodynamics, whether at the lab scale, if we kind of look at a bubbling fluidized bed regime, does it translate to, if we want to be operating at a turbulent regime at the larger scale, should we be keeping the fluidization regime the same? Do residence time matter at the different scales? Does the Geldof group matter? Because if we think about scaling laws, then the particle size and the reactor diameter, there's some relationship. Does that mean that we use a smaller particle at a smaller scale and then a larger particle at a larger scale? And then the mass transfer back mixing, all these are very, very difficult to scale. And that is why these challenges for scale up still continue to bother the community. So then for the past couple of decades, CFD, computational fluid dynamics, has advanced very, very rapidly, and then confidence has gradually grew. And then in the 1990s, the US Technology Vision 2020, they have already set out this very bold vision that we can do scale up very, very quickly if we can rely more on computations, because it's faster, it's cheaper. Arguably, it's faster than doing the experiments. So this bold concept of commercialization with reduced need for experiments basically motivated a lot of academics to try to kind of think about, can we be describing these processes using first principles. If we have first principles understanding, then we can just apply it directly on a commercial scale, then it'll be perfect. So this kind of very bold vision set forth a lot of more improved experiments, a lot of improved models. But it's 2026 right now. We know that although this understanding database and tools have advanced very, very rapidly, scale up still rely a lot on so CF with. And so then in the kind of 1990 to right about 2005, so then if we kind of look at the scale up, so scale up is still dependent on these few steps. So the CFD models have advanced very, very rapidly, but up to 2005, right about there, the application is still mainly academic. The application at the commercial scale is very, very limited. But then because of this kind of advanced or more kind of more knowledge that we have through the years, we have a lot more confidence at each stage. But the number of stages, the years involved, is still remain more or less the same. And then if we kind of move on to 2005 onwards, this was right about when the CFD software became more embraced by industry. So then they are like, okay, we can this has been developed for decades. We can now kind of try to see how we can use this to speed up scale up. So models improved and confidence in model predictions grew. So then the contemplation of, okay, can we do this shorter now? Can we skip one of the steps? And then if we skip one of the steps, we save a few years, we save a few tens of millions of US dollars. So that became like something that people started becoming more confident about. And then what about tomorrow? How can we do this even faster and even cheaper? So then, of course, all of us know that AI ML has been going around for kind of a couple of decades at least for now. And so this data analysis, design of experiments, equipment design, flow sheeting, risk assessment, reactor models can be done a lot this can provide a lot more confidence into each step. But then with the industry, there's still a lot of resistance, or there's not enough confidence to say, okay, now we can very confidently skip a few steps. So it's really still about giving each step a lot more know-how and understanding rather than being able to skip any step still. But then we can, as the academic community, think about, is it possible still? Like it's not possible a few decades ago with the US technology vision, but can we now get enough confidence to skip a few steps? Can we simulate the commercial scale reactor with a lot more resolution and with a lot more accuracy now with all these new tools we have at hand? So then kind of thinking about what we can do. Of course, machine learning, artificial intelligence, we have a lot more confidence in these tools right now. And then we know that even purely data-driven models, it can provide us with more mechanistic understanding, more predictive capability. And then, of course, then the gray box models that I'll talk about in more detail later, can we hybridize some incomplete understanding, but some understanding with black box models and be able to have more confidence in scaling up these processes. And then AI-driven optimization in terms of equipment design and flow sheet. Right now, these are basically based a lot on experience and empirical heuristics. So can we use AI to do this a lot faster? So we kind of contemplated all these kind of a lot more applications with regards to AI that we can be used implementing in industry kind of various aspects. We did a review recently. And then with regards to equipment design, this has already been made possible. This is a Siemens kind of software. So just based on simulations like CFD-DEM, we can run simulations, give it an objective function, feed it to this SimCenter Heats software, and then feed it into a design engine and keep looping it to design a cyclone, which is still a very unit operation that's very important for fluidized beds, but very incompletely understood. So then the problem is that if we want to use AI and machine learning to be doing scale up, of course the industry has to embrace it and endorse it, which means we gotta have enough confidence first of doing this. So then the Siemens industry survey, this was very recently, it was just last year, on the process industry, these are the numbers. 40% still do not trust AI. And then 74% say, okay, we can use AI, but then we do not have enough good quality data. So these are still very stark numbers. But this is analogous to kind of the growing pains of CFD. So commercial CFD software was only embraced in right about 2005. And this was after decades of development in academia. So potentially, if we can give more confidence to AI ML, this could, within a few years or within the decade, we could potentially have industry also embrace this as a useful tool. So then let's talk about okay, scaling up is slow because we have all these challenges. But then we try to kind of summarize it. It's very wordy, but with Brooke Van Omen from Delft, we try to think about why is it that after more than 100 years we are still struggling with fluidized bed technology. So we kind of summarized it into five different points based on the different scale of fluidized bed. So on the particle scale, we're thinking physical properties is still a main challenge. And what is the problem here? So earlier, particles used to be supporting particles. We are talking about these particles being inert or catalysts. So they are just they play a supporting role. And so because they play a supporting role, we are able to select, or we can make them the way we want to. So we can select the more fluidizable Geldot groups A and B. But then increasingly now, when we think about nanoparticles, biomass, and plastic particles, these particles are now increasingly the feedstock or the final product. And so when they are the feedstock of final product, they are the main, they play basically the key role in this fluidized bed process, and they may not easily fall into these easy to fluidize Geldart groups. And this is the problem. Hence, we can't tailor make them as easily as previously. So this is one of the kind of a challenge that is kind of more so because previously the fluid catalytic cracking catalysts, these are all made to be group A and they're very, very easy to fluidize. But now we cannot choose the particle size. We have to be able to fluidize these in the fluidized bed process. The other thing is the chemical properties. And this, of course, the chemical properties affect the key physical properties such as density, surface energy, inner particle forces. And with these advanced particles, we are talking about these core cell catalysts. With the catalytic community, they want to improve or basically reduce the amount of catalyst that's used. So they basically just have the catalyst particle on the surface where it's needed or where it can and basically within the particles, we don't need the catalytic properties, so then we can save on the materials and the cost of these catalysts. Or coated, there's the atomic layer deposition, or with food and pharmaceutical particles, there's these binders. So then they could be sticky and they could be increasingly sticky as we try to coat more and more of these binders in the pharmaceutical industry. Or cathode with the batteries, these evolve as these processes continue. And then, of course, then we also have the carriers with the chemical looping, like the oxygen carriers. So these have evolving properties. So we may need to fluidize them differently in the air reactor versus the fuel reactor, for example. And then flowability on the larger scale, the flowability and fluidization quality. This is related to the kind of the new particles that we have to be fluidizing now. For example, the nanoparticles in the pharma and food industry. So these have excessive interparticle cohesion, van der Waals, liquid bridging, electrostatics, and these can lead to severe agglomeration and even defluidization. And then, although we think that good flowability means higher fluidization quality, this may not necessarily hold. So then when we think about scale up, we have to also think about this correlation between flowability and fluidization quality. And then on the even larger scale, the sustainability aspect of it. There's of course, fluidized bed technology has significant potential for clean energy and circular waste processing. But then with these processes, increasingly we have challenges of feedstock heterogeneity. If we get plastic waste, can we always ensure that the plastic waste we get are always of the same quality? The same case with biomass. Can we always get the same kind of waste to feed into these fluidized bed processes? That is increasingly challenging. We used to have like just catalysts, right? We buy the catalyst from, say, BASF, and we know what to expect. But now with these waste treatment, this is not so straightforward. And then material durability, process complexity, and so on and so forth. These are becoming more challenging. And then with safety, we also think about these harsh conditions, high temperatures, high pressures, chemically aggressive environments. And then all these are still, it may not be so important, but now it's getting a lot of attention with kind of dust emissions, with kind of handling these particles. If we try to get samples from the reactor, it's not so trivial. And then hygiene, environmental emissions, all these are adding on to the challenges that we need to be addressing when we think about how to implement a very promising process on the commercial scale. And then we also thought about, okay, now we know the challenges. What are the tools available that will help us with addressing these challenges? We have the sensors and measurements. Unfortunately, we do recognize that pressure and temperature for the last century are basically the only instruments in these industrial fluidized beds. Although all these like very, very fancy thermography and tracer methods have been developed and a lot of soft sensors too, but these are still largely only in the labs. Soft sensors could be promising. So based on temperature and pressure measurements, we could use these algorithms to try to get more information from these already installed instrumentation. We've also talked about assistance methods. How do we increase process efficiency, enable nanoparticles to be fluidizable, and then facilitate supplementary or intensified functionality? Models, we'll talk more about this later on. Multi-scale models. The problem is, as I guess this community knows very well, is that the macro scale performance is dependent on the mesoscale structures, which is dependent on the micro scale interaction. So these are the various scales, and it's still not we are still not able to fully resolve the mesoscale structures. And then the problem is that with these industrial fluidized bed reactors, we are talking about the order of 10 to the power of 12 to 10 to the power of 15 particles, right about there. And this is definitely still beyond the current modeling capabilities. So we're looking at a trade-off between resolution and computing cost. And then for AI and digitalization, so we do have a lot of kind of soft sensor methods being implemented right now. And then, but these fully autonomous reactor design optimization or plant-wide digital twins, these are still mostly academic. And then this is because, not because, this is also partly because of this data availability challenge that Siemens has identified, and then integration complexity, regulatory requirements. In the EU, there's this EU AI Act that just got rolled out in 2024, right about there. So there are more regulations that we need to be kind of addressing rather than kind of brute forcing things through, even though we know they're good, and then a lot more stringent safety considerations. And another enabler is if academia and industry can work closer. So then the problem is that there's usually a discrepancy of time scale and a discrepancy of goals. Industry usually want things to be solved like now, and academia would think about, okay, a PhD student, so what can a 4-year project look like? And then also the priority. So in academia, maybe papers are important, but industry, the focus is not so much on publications, for example. And then of course we know that with any kind of collaboration, the paperwork regarding the non-disclosure agreement and all that takes a really long time. So these are good enablers, but then we know it still takes some time for them to be fully used for scale up at the commercial scale. And so in summary, the outlook is that we know these challenges. It's not because we are not making progress. It's because the fluidization, the particles we have to be fluidizing, or the fluidization process is getting the changes in the challenges that we have been addressing through the decades. And then we thought about all these enablers that potentially we could be rolling them out if we get more confidence in the information that we can get out of it, and then while taking note of all the safety regulatory considerations. So then kind of the goal is to make fluidization technology progress from an empirical art towards a predictive, reliable platform for circular and low carbon technologies. So then we thought more about, okay, so we can use modeling to enhance or expedite this scaling of industrial multi-phase reactors. But how do we go about doing that? So kind of rethinking back to this 1996 roadmap for the US chemical industries, this technology vision 2020. And so just a quick reminder that this involves, or this is in the US, the industry, the academic and the national labs came together, and then they want to try to transition towards a computationally assisted scale up so they can go a lot faster. So if we kind of think about what are the limitations, there are these twin challenges. It's not only about the algorithmic accuracy. This is with regards to the incomplete physics that we still are trying to bridge especially in a lot of academic groups. And then the other is this hardware limitation. Right now with CPU, GPU, because it's based on bits, we are increasingly, basically right now the limits is not with how fast we can do these calculations, but it's with the memory bandwidth, or in other words, the data movement is now dominating CFD runtime. So how do we kind of overcome these two challenges simultaneously so that we can do this a lot faster? So we kind of reviewed this evolution of models. We went from empirical fitting very, very long ago to reduce order models, and then to higher order models, to AI hybrids, to quantum, and eventually we think we'll be moving towards a quantum hybrid. So let's kind of think about how much faster we are doing things now. So with these AI-based reduced order models, we are able to get 3 orders of magnitude acceleration while maintaining agreement with high fidelity CFD. So AI-based reduced order models has been proven. And then these physics-aware models, where we try to hybridize physical understanding with black box, these have proven to enable speedups of over 100 times over CFD and about 10 times over CFD DEM. And the exascale, this is enabling 10 to the power of 9 and 10 to the power of 10 cells. And then we kind of remind ourselves in the industrial fluidized bed reactor, we're talking about 10 to the power of 12 and 10 to the power of 15 particles. But we are moving towards there. So this is already, exascale is already enabling a lot more cells towards this industrial scale processes. And then quantum hybrids right now is still a single phase concept. So it has been reported that the scaling can improve from polynomial qubit to logarithmic with respect to system size. So this indicates that when this quantum becomes more mature, we could potentially have orders of magnitude speedups for future quantum native CFD. So let's so basically this the model has advanced significantly, and now we have as proven orders of magnitude. We can do things orders of magnitude faster than what we used to be able to do. And then we're gonna talk a bit more about this HPC hardware, the progression. So the problem, as I kind of alluded to earlier, is that the limits are this data movement. And with bits, we are really limited by this, not by how fast the calculation can happen, but the data movement between the bits is now dominating CFD runtime. And even with NASA's CFD Vision 2030, in a few years, they're predicting that this high resolution simulation for single phase applications would still be impractical. We are still not able to do this by 2030. So that is the limit of current HPC. And then, of course, with the current HPC, it is mainly made up of CPU and GPU. And a lot of papers have tried to do this load balancing, because although GPU is supposedly faster, it cannot do everything. So there are a lot of papers kind of reporting on what do we do on CPU, what do we do on GPU. And then for GPU acceleration, speedups of 2 orders of magnitude have been enabled, kind of trying to load balance between CPU and GPU. And so with a QPU, with the quantum, it's very, very promising, because we can move away from bits and rely on qubits. Qubits allow for superposition, parallel processing, entanglement, and so it allows for allows us potentially to do things a lot faster, overcoming the current limits that's dominating CFD runtime. So the problem though with current quantum processors is that it's still limited right now to comparatively small and noisy systems. Right now we're still in the NISQ era, so we need to move away. But then the IBMs and all the NVIDIA, they are working on this quite actively, and so it's supposed to be ready within the next 5 to 10 years. And then, as the hardware develops, that's probably out of our domain. These quantum algorithms have to be developed in parallel while we await for the hardware to be ready. So these quantum algorithms right now, there's a lot done on trying to overcome this noise and this error. But then when they become ready, this quantum CFD algorithms, if they are ready, then we can very, very quickly make use of this quantum platform. So then in future, we think it's going to be a judicious weighing of CPU, GPU, and QPU, relying on the different kind of advantages that each of these hardware can provide for us. So a little bit about quantum CFD. These are all very, very new papers, 2024, 2025. So quantum CFD demonstrations have been achieved for single-phase flows. It has not moved towards multi-phase flows yet. So for the current noisy quantum hardware, people have reported these quantum routines accelerating specific linear substeps within the classical CFD loops that we are very familiar with. And then with the less noisy quantum hardware, as they become ready, then potentially these larger PDEs can be offloaded to this quantum hardware. And then we can do more with the less noisy quantum hardware. So then right now, as you can see, this is from this paper right here, with classical CFD that we do. So this is simulation time versus grid size. We know that as we increase the number of grids that we use, the cost increases very quickly. With the quantum, this is the projection that we are able to, as we try to simulate more and more grids, the cost will flatten out with the number of grids that we use. So this quantum hardware promises to overcome the CPU, GPU limits. So I'm gonna skip a few slides because I see that I'm kind of I'll kind of talk about this gray box modeling, and so this is about knowledge data hybrid. So with the white box that we are this community is very familiar with, CFD, CFD-DM, MP-PIC, DNS, and so on and so forth. The problem that we know is that the computational cost is very high. And then with the AI, where we basically just throw data in and get results, the data cost is very high. So with these gray hybrids, if we kind of hybridize some mechanistic understanding with neural network or with some sort of AI model, then we are able to have a trade-off between computation cost and data cost. So I'm going to talk more about that. So this gray box modeling is basically trying to hybridize the physics-based models with the data-driven models. So this provides a trade-off between the high computational cost of white box models and the high data cost of gray box models. And then we can have different model grayness. If we have a lot more mechanistic understanding, we could have it less gray. If we have a lot more data, we can have it to be grayer. So then we can try to at least have some physical governance to these processes that we know are very governed by physics. So a neural network has been shown to provide over 1,000-fold speed up over conventional CFD. With a physics-aware neural network, it requires at least 15% more time than neural network. So it's slower than pure black box, but then these offer a lot better extrapolation capabilities. So there are some examples of gray box models. There are various ways to do it. We could basically have our black box and our physical equation, and we minimize the loss concurrently, and basically then it will have both understanding within this model. Or we could have set it as an equation with a physical component and a data-driven component, and hence again we can make use of the data-driven the regression capability of this data-driven component, and also force some physical understanding into these models. So then the question to ask is, can gray box models enhance interpretability and generalizability? I'm gonna maybe skip to the bubbles since maybe it's more relevant to this community. So with bubble size, we try to kind of think about, okay, if we try to kind of use these on bubbles, bubbles are these mesoscale structures, and they dictate, they govern the performance in terms of residence time, in terms of the mixing within the bed. But then if we kind of try to measure these bubbles, we know that these are very, very noisy. So this is a data set that has been reported. So this is bubble diameter with respect to column height. And as we, for those of us who've tried to measure bubbles, we know they're very, very noisy. And then near the distributor plate, we could have a there could be some surprises with regards to the bubble behavior. And if we kind of look at the distribution, they may not be normal. So these bubble data are very, very noisy, and that is maybe a problem for black box models. And then on the other hand, with mechanistic understanding, there's no first principles description of these bubble growth. So then the question that we try to address is, can empirical correlation be used for physical governance? And this is based on that whenever these professors come up with these empirical correlation, it's not just random, right? They have some physical understanding, or these parameters do mean something. So we are like, can we make use of this? Something physical understanding is not perfect, but can we use this to govern these gray box models? So then if we kind of look at this plot right here, so this is bubble size versus height. And so if we just apply the empirical correlation, it very, very significantly over predicts. And this is because we know that bubbles should grow with height. And this correlation basically overdid it. And this is also because probably this data set was not accounted for when they developed this correlation. So if we use a pure neural network, a black box, you can see that it doesn't reproduce the bubble growth with a bit height very perfectly. But then if we marry this empirical correlation with this very noisy data, what we can see here, this red line, is that it adheres to this physical understanding that bubbles should grow with height, and also try to obey or try to observe that the data is like this, and so the bubbles are not growing as fast as the empirical correlation is predicting. So this would improve the generalizability of this to more data, basically expand the scope that this empirical correlation can be applied to. And so then we can further look at how, into more detail as to how this data-driven correction can improve model robustness. What this is showing is that with this orange slide, this is the empirical correlation. It severely over-predicts the bubble growth. So we can use the data-driven component to correct for this over-prediction of bubble growth so that it can respect the data more. And so then we also looked at, so if we try to kind of then apply it to more specific data sets, to the very narrow particle size distribution and to a very broad particle size distribution, we can then see that this, with a very broad particle size distribution, which are probably not tested when they develop this correlation, but then this basically, the model is telling us that, okay, this was not accounted for in the empirical correlation. But then we can basically correct, we can use the data to correct the model and still have the model kind of be able to adhere to the data set more accurately. So although this, with a very, very broad particle size distribution, which are not accounted for in the original empirical correlation development, we can still use the data to correct for this model and improve the predictability that way. So then, in a nutshell, basically we have applied gray box models to bubbling data, and then we try to extend the utility of the empirical correlation by using the data to correct for these equations. I'm going to skip all the way. I could share the slides later on, but then in conclusion, we just want to say that the current fluidized bed reactors or multi-phase reactors are a lot more complex than, it's not because there's no progress, but then it's because these are getting a lot more complex. There are a lot more additional considerations, more complex designs, energy, environment, safety, risk, waste, health, emissions, more diverse markets, more complicated particles, and so on and so forth. And as we think about these new tools that we can use to do scale up faster, we want to kind of emphasize that domain knowledge remains non-negotiable. It's still very, very important. Even if we use ML AI, we still need to know what kind of understanding or whether the predictions make sense. And high quality data is very important. We need to be measuring the right parameters correctly. And then with this, and even if we try to say, okay, AI is the answer to everything, there's a lot of understanding that needs to go into this model architecture with the different neural network, with the hyperparameters, with the scaling. And then this is the final slide. So we are thinking that in terms of kind of trying to expedite these fluidized beds scale up, we can learn from the past and build adaptive models. So then these are kind of newish development, this cross-graining filtered as trade-off between resolution and fidelity. So now we could kind of think about AI-assisted cross-graining, adaptive layering, mesh refining, and then regime-aware closures. This is hybridizing AI. And then the emerging computing architectures, we know, GPU acceleration, exascale systems, these are already ongoing. And then this cloud-based deployment is now enabling, even if we do not have access to these pretty specific HPCs. For example, Google lets us use the GPU for free. So then it's being democratized. And then for gray box modeling is AI alone may not be the answer, but if we can bridge our domain know-how with AI, then this physics-aware models may be may give a lot more confidence to industry that we are not just feeding it. We are just not just using data, but we are kind of infusing it with our understanding. And then the quantum subroutines, this is the hardware that's up and coming. And so we need to have these hybrid implementations, quantum classical CFD routines, and this could be a very strategic accelerator within a few years. So this is what I've talked about today. Thank you very much for your time. I just have one final slide. So we have a new fluidization textbook that just came out. It's called Fluidization Processes, Design and Operation. This is not meant to be a replacement of the very, very, very good textbooks that are already out there, but the new dimension that we are adding is kind of the design part, because we realize that for a lot of these textbooks, you could know these core fundamental concepts very, very well, but you still cannot be designing a fluidized bed reactor. And this was the gap that we were targeting to bridge. Thank you so much for your time.
Thank you, Jia. Thank you. Wonderful overview of challenges and enabling technologies. Very, very nice, very inspiring talk. Thank you very much, and congratulations for the new book. Very much needed. We look forward to having a look at it. Now it's time for questions and discussions. I think you've covered many topics. So, for example, we have already two questions from the chat box. I'm going to read it. One from Professor Yao. So, regarding AI, could you please introduce the latest AI level in the world for fluidized bed shortly? This is a quite broad question, maybe. So, just touch on what can currently be done in the area, in the fluidization topic regarding the help AI is giving in the field.
Let's go up to so we recently did this review to try to basically on the industrial level, how we can think about here kind of the various kind of aspects that AI, we're talking about chemical engineering, but kind of process engineering, fluidized bed is one of the processes, how we can, what tools are already available. So this generative AI in terms of equipment design, definitely infusing a lot of understanding into these AI models. And then there's this the process control part, this machine learning operations, and then there's data benchmarks that are available. We can make use of them. And then even in terms of kind of thinking about the sustainability and this life cycle analysis, or the TEA, right, the techno-economic analysis, these all can leverage AI. And then the governance standards and regulations, we need to be abiding to them. And the US has put out one, and the EU recently also put out one. And they also talk about, we also kind of emphasize that education and upskilling of current engineers, and the education of our new up-and-coming engineers is very important. So this is a review that we did recently, trying to contemplate how AI can be used in process engineering. I hope that answers the kind of question.
Yeah, I think with the time available, that gives a nice overview. There is another comment and question. I'm going to read it. So the fluidized bed process is highly complex, and the coupling technology of flow field, physical, and chemical reaction field is as intricate as you described earlier. Many technologies still require further development and remain somewhat distant from industrial applications. How do you perceive this challenge? Do you believe AI will help us to solve most of the problems? Maybe you partly already answered along the way. This was asked early in your presentation. So would you like to comment on how, again, AI is making studies closer to industrial applications?
I think maybe gray box modeling could be a way for us to implement it more, because as the Siemens survey kind of indicated very correctly that, and then in my previous job with the industry, the AI is not that much trusted because they feel that it's a black box. So then there's this thing about industry doesn't trust AI. So then perhaps then if we can kind of think about gray box models, trying to infuse AI with fiscal governance, these would give us a little more confidence. Industry there could be a lot more confidence that way. And then with this data related challenges, it's really about kind of developing a easy to implement kind of experimental or observation tools, or it could be like soft sensors and all that we could have. But then yep, maybe more. I would think that gray box models, basically infusing it with our domain knowledge and trying to think about with the existing observation measurement data that's available, how do we make better use of it, or what better measurements should we be recommending be made? Possibly.
Yeah. Fully agree. If I may say, thank you. There is a question in the chat box that is written in Chinese characters.
I already transferred the Chinese to English below. Yeah. You just go to Outlast. Yeah.
Okay. I'll skip the Chinese and then go to the English. Okay. There is quite a quick question, a request for information from Taiwo Adedeji. Can you please give us a link to the book here? So if you could.
It's
just published by Wiley, actually. Yeah.
This is the QR link.
There is a QR code there. And then, so the one question was how to establish a new scaling criterion for fluidized beds that balances local hydraulic similarity, for example, radial distribution of gas holdup, with global dimensionless number matching, enabling precise replication of flow patterns and performance from pilot scale to industrial scale application. Again, is on the large scale side where we all probably know little about ways to scale up.
With the scaling up, so that's exactly the problem. Are we looking for hydrodynamic similarity, or what do we define as hydrodynamic similarity? I mean, this is still a kind of, I think, still very unknown, right? Because when we think about, okay, so the Galdup group, if we kind of test these Galdup groups, there's been a lot of kind of these failure cases, right? And that is a lot is based on, for example, in Texas, right? This was like in the maybe right after the war when fluidized bed was getting a lot of attention. They in the small for Galdup group B particles especially, right? In the lab scale, you get a lot of slugging, so you get a much different residence time. But on the larger scale, slugging is not a problem generally because this it's so big, the commercial reactors. So there's been a lot of these cases where people assume that whatever is tested on if we use the same particles, then maybe we can scale it all the way up. But that doesn't basically, we have to think about, do we want to keep the residence time the same? Because then if you have slugging versus non-slugging, it's very, very different. And then do we, like what kind of hydrodynamic similarity are we wanting to keep in focus? Because that might be different for different applications and different reactions. So I think maybe a puristic scaling law might not be applicable for everything, potentially. Not really. Yeah, my take at least.
Yeah. Excellent. Okay. And then we have another question on slide 7. If you can, in the meantime, find slide 7. Do these images represent actual industrial fluidized bed system, or are they purely schematic diagrams?
We were trying to present the different scales of it. So basically on the larger scale, it's more complicated with a lot more cyclones to kind of retain the particles. And then on the bench scale, sometimes it's not even a fluidized bed, right? It could be a packed bed reactor because it's the easiest for a chemist. Usually it's the chemist, right? The chemist to understand. And so these are kind of trying to it's not applicable for all the ranks. So this is like probably a turbulent bed. So if you have a bubbling bed, you don't need the cyclones. So it's basically kind of looking at the scales and the complexity at the different scales.
Yeah, so probably the last one is representative of an actual industrial scale, commercial unit.
It's a turbulent, yeah, this is for a turbulent fluidized bed regime. So if you have bubbling, you don't need the cyclones. If you have a fast fluidized bed, you may not want to design it that way. For example,
we can read ammonia and propylene, so it could be associated.
This is for this is for acrylonitrile. I think we drew this out. Oh, Ray drew this out for acrylonitrile process.
And it has all the internals that one could expect from a commercial unit now, with the exchanger tubes and cyclones and the sparge and the grid and whatever. It's very well representative. Thank you very much. There is one more question. For different types of fluidized beds, bubble, recirculating, and turbulent, how to establish a unified scaling prediction methodology system that simultaneously ensures engineering design feasibility and prediction reliability. This is also very challenging, very nice desire. I'm sure in the book that you've published, that you just published with Rai Coco, there are a lot of answers to this very big question.
I think that is what all of us collectively are working towards answering. This is the grand research question. How do we have a unified way of doing this quickly and cost effectively?
Yeah, so I find it interesting that the first part of the question regards design feasibility. Even feasibility is at question when you scale up. Sometimes not only, let's say, performance, they may degrade, but you may end up also even with an unfeasible design when scaling up. And this also gives an idea of how complex the process of scaling up can be.
Yep. So we put out this because we think that, like, even when it comes to designing, say, the distributor system, there isn't anything out there that kind of talks about what to look out for. Like if we want to be designing the distributor, and then if we think about cyclones, this is really all of these are basically an art more than a science, right? There's so many different ways or different rules of thumb that different engineers would swear by, and then it's really just out there. So we kind of think, put it in terms of like what to look out for. So even if you don't have the perfect equation, you at least know what is wrong with it.
Okay, I see no more questions. It was an excellent talk, a very interesting discussion. So thank you very much, Professor Chu, for this inspiring talk.
Thank you so much.
Thank you very much.